Empezamos. Cuando quieras.
Okay. So good morning, everyone, and I'm sorry for the circumstances. I had to take measures due to COVID, a possible COVID infection, and okay, I will start presenting now. Can you see the slides?
Yeah.
Can you see?
Yes. I'm going to.
I cannot hear you.
I'm going to mute
Okay.
the mic.
Okay,
So,
then I will start.
okay. The questions are at the end, so we don't have to do
Okay.
crazy things.
Okay, so I will present to you today the work that we've been doing in open-air microwave entanglement distribution. This is the work that we've been doing for the QNX project of the European flagship project, and it's basically trying to extend the knowledge of quantum communication into open air and explore the challenges of doing quantum communication in open air. Since quantum communication can present an advantage over classical communication, an advantage in security and efficiency due to the presence of entangled resources and the effective use of these resources, then we were considering, that the first step to be taken here is to explore entanglement distribution or the distribution of entangled resources through open air. It has many problems at first, like how does entanglement behave out of cryogenia, out of the very low temperatures in which entangled states are generated? How can we implement an efficient line of quantum repeaters? And how can we do this with microwave technology? And why microwave technology? Because it presents lower atmospheric attenuation of the signals and lower energy scales than in the optical regime, which is the regime that has been naturally studied for quantum communications, and especially because it's the natural talking frequency for superconducting circuits and superconducting quantum technologies in general. So these can present advantages, for example, in distributed quantum computing, trying to build smaller quantum processors or quantum processors with lower number of qubits and then connected them. Can be connected with waveguides, or they may be connected through open air. These can also find applications in satellite quantum communications, and that could then maybe lead to the quantum engine. So this talk is going to be divided in these parts. First, we need to define what the entangled states, the entangled resources are going to be. Then, as I said, they will be generated in cryogenic temperatures, so we need to find an antenna design to try to connect the cryogenic environment with the open air. It's going to be basically an impedance matching problem. Then once the state is in open air, we need to characterize the losses that it's going to suffer, and we will do that through an attenuation channel, and then we will try to overcome these losses and try to improve the state after these losses have been effective, have taken effect into the state and entanglement of the state. And apart from entanglement, we will study the simple case the paradigmatic case of quantum teleportation, because you can have entanglement in state has to be or can be used for different protocols, and we need to take into account that efficiency of certain quantum communication protocols does not only depend on the entanglement of the state, as we may see later. So the first thing, entangled state generation. In the microwave regime, entangled states are easily prepared using what is called Josephson parametric amplifiers. These are transmission lines that are terminated by squid. squid is just two Josephson junctions in parallel, or they can be terminated by the squid with the capacitor, as you can see in the image. And the idea is that energy can be, or energy pumping into the system can be achieved by threading a magnetic flux through the squid, and depending on the frequency of that, the change of that magnetic flux, you can achieve squeezing. Squeezing means that in phase space you're going to reduce one of the quadratures of the state below its natural value while amplifying the other, right? In this particular case, in which you set the frequency of the pumping as to be twice the natural frequency of the transmission line, then you can achieve squeezing, and in certain regimes you can achieve phenomenon in which an endless signal is generated at a different frequency from the signal, your input signal. And if you're able to set the frequency of your state close to or equal to the natural frequency of the system, you find yourself in having parametric down conversion, which is the spontaneous procedure or process in which one photon suddenly breaks down into two. And this Hamiltonian describes then the single mode squeezing operator. So the propagator with this Hamiltonian describes the single mode squeezing operator. And with single mode squeeze states, we can obtain something that is called a two-mode squeeze state, that is an entangled state. And it's also a Gaussian state, right? Combining two single mode combining two single mode squeeze states through a 50-50 beam splitter, you can achieve a two-mode squeeze state that is entangled, and then you have some local rotation that you can undo. As we have seen, this operation is Gaussian. You have initially Gaussian states, you have vacuum states, or you have thermal states, maybe due to non-zero temperatures. You have a Gaussian evolution because quadratic Hamiltonians imply the preservation of Gaussianity. Also, the beam splitter is a symplectic operator that preserves Gaussianity. So the two-mode squeeze state that you find at the end is a Gaussian state. The Gaussian states can be fully described by the covariance matrix. So the entangled resource, entangled states that we will be using will be described by the covariance matrix, and they will look initially like this. This is a two-mode squeeze thermal state. It takes into account the fact that JPAs do not work at zero temperature, and there will be some thermal noise present, so they will consider that the input state here, instead of being a vacuum, is going to be a thermal state, right? And a thermal state with this small n number of thermal photons. Here R is the squeezing parameter. So it is the real part of this guy in the single mode squeezing operator. Now, a thing about, maybe I can go through this quicker. The thing about Gaussian states being described only by the covariance matrix, also you need the displacement vector, is can be exemplified by this. You can write the characteristic function of any state in this way. This is equivalent. You can write the density matrix using the characteristic function. For Gaussian states, the characteristic function looks like this, where this sigma, capital sigma, is the covariance matrix, and this D is the displacement vector. D contains all the first moments of the state, and the covariance matrix contains all the second moments. And this is the only thing that you need for describing a Gaussian state, any Gaussian state. And this characteristic function is a Gaussian function, and is the Fourier transform of the Wigner function. So you know, the covariance matrix can be characterized by these two inequalities. It has to be positive and has to satisfy the uncertainty principle in this way. This omega is a symplectic form. You can find it here, and it's associated to to the the commutation relations of the canonical variables. So same as or similar to how any Hermitian matrix can be diagonalized by unitary transformation by any unitary matrix, there's Williamson's theorem for covariance matrices that says that any covariance matrix accepts a symplectic diagonalization or can be diagonalized by symplectic operators, which is equivalent to a normal mode decomposition. So this allows us to find these quantities that are called the symplectic eigenvalues of our covariance matrix sigma, that are the eigenvalues of this matrix, or the absolute values of the eigenvalues of this matrix, and they are always smaller or equal to 1. This comes from the uncertainty principle. For two-mode covariance matrices, such as the one that we present here, we can easily compute the symplectic eigenvalues in this way. So here, this is called the Saralian of the covariance matrix. This is the determinant, right? I'm showing you this because with the symplectic eigenvalues, we can compute the negativity of the state, which is an entanglement monotone. It's something that we use to quantify entanglement of the state. Same as when you apply partial transposition to a density matrix and you look for negative eigenvalues in order to say that the state is entangled. Here we will compute the symplectic eigenvalues of the partial transposition and use them to compute the negativity. So if you do partial transposition on the covariance matrix, you get these new tildes, right? And this delta tilde, the only change here is the sign of this. And then if any of the smallest symplectic eigenvalues of the covariance matrix is smaller than 1, then you will have that the negativity is going to be different from 0, and then the state will be entangled. For the case that I've shown you before of the two-mode squeezed thermal state, this is how the smallest symplectic eigenvalue after the partial transposition looks like. So okay, moving on. Now, we have described the states that we can generate and characterize the entanglement of these states. We have to look now at the quantum antenna. The antenna, as I said, is going to just serve an impedance matching problem. We need to match the impedance of the cryostat to the impedance of the open air. This is just going to be a cavity with changing impedance depending on the position that we have optimized we have studied in a previous work, finding that with some DMRG inspired optimization techniques in which we divide the cavity in very small slices and then assign an impedance to those slices and optimize sequentially, so starting from 1, then finding the optimal value, then going to 2, and then doing that, and then going backwards. Then we find that the optimal impedance has an exponential shape, which is the thing that you find for classical antennas. When you're looking at maximum or maximizing the transmission, and we're able to obtain reflectivities in the antenna that are smaller than this value. So for very small reflectivities, we can obtain a formula of how the smallest symplectic value of the partial transposition changes after the antenna. It's related to reflectivity and this end thermal, which is the number of thermal photons that characterizes the environment to which the cryostat is connected through the antenna, right? So this is basically the thermal noise that is coming through the termination of the antenna and mixing into the state. Now, once the state is in open air, we will use an attenuation channel to describe losses, both absorption losses and thermalization, right? Essentially, what we're going to do is treat this attenuation channel as a beam splitter with reflectivity given by this formula. This mu is is like represents density of reflectivity. It represents well, it's an attenuation parameter essentially. What it represents is number of photon losses per unit distance, right? And L is the distance that the state has traveled. So if we combine the antenna, describe the antenna also as a beam splitter with this thermal input, this attenuation channel also as a beam splitter with the same thermal input, we can combine the action of both beam splitters and find the reflectivity of an effective one and see how the state changes with this dissipation mechanism, right? So essentially we're considering that Alice generates the state and sends one of the modes through the antenna into opener, and the other mode she keeps in her cryostat. So essentially this is the mode that is unaffected, and this is the mode that becomes where it's affected by thermal noise, right? So this is the reflected thermal noise that comes into the state, and this is the transmitted part. And these are the off-diagonal elements of the covariance matrix that represents the correlations in the state are also affected by this mechanism. But I mean, this is the one way to look at this problem, right? The case in which Alice generates the state and sends to both. But there's another way in which you can reduce or you can balance the distance that the state have to travel through open air. And this, considering this case here, that is what we call the symmetric case, right? This state is the one that we have seen. If we compute the negativity, we see that the maximum distance that the states can travel before losing entanglement is about 345 meters. In the symmetric case, we have that this distance is about 300 meters. The problem is that we're considering for these perfect antennas, but in reality, I mean, probably it's not going to be the case that we should consider. Now, okay, now that we have seen how states degrade in open air, we need to look at some ways to overcome this entanglement degradation. And these are entanglement distillation and entanglement swap. So the idea about entanglement distillation is increasing the entanglement of a given state. That most entanglement distillation protocols have many problems. The first one is that they are not deterministic. Also, they normally require many copies of the same quantum state in order to increase entanglement, and the resulting states are generally non-Gaussian. In this case, we did look at an entanglement distillation protocol that does not require many copies of a state, but does have the other two downfalls. It's called photon subtraction, and basically it's what it is. You're just subtracting one photon in each mode of a quantum state. As you can see in this figure, this represents, the generation of two-mode squeeze vacuum states through JPAs. Then what we would do is to send each of the modes through a high transmittivity beam splitter, combined with some ancillary states, vacuum states for example, and then measure or count the number of photons that you get reflected, right? When you detect that a photon has been reflected here, then you postulate the state and you keep the state in which you have detected a photon. It is basically an adaptation of a very well-known photon subtraction protocol as normally done in the optical regime. This would be the probabilistic photon subtraction, right? You have a certain probability of a photon being reflected in the beam splitter and then measuring it and keeping the state. If you do it heuristically, you just apply annihilation operators on the mode, and that's it. Just looking at the simple case of the two-mode squeeze vacuum state, see that the negativity is given by this formula. Here, lambda is the hyperbolic tangent of the squeezing parameter. and so it's between 0 and 1. If you do photon subtraction heuristically, you subtract 2 k photons in one mode and k photons in the other mode for 2 mode states, then you get this formula. If you do it probabilistically, this formula is just modified by the transmittivity of the Green split, which is given by tau. As you can see here, heuristic photon subtraction is much better than or gives much larger negativities than for the original state. Original state here is in green. The dashed lines, blue and red, represent heuristic photon subtraction. 2 photons for red, 4 for blue, and the dashed and dotted line represent the probabilistic photon subtraction with 0.9 transmittivity. So, okay, so far for photon subtraction. As you can see, works better for lower squeezing, since you have this probabilistic nature, it's not going to work always. If you take the tau going to 1, then you're going to recover the heuristic case, but the probability of detecting photons goes to 0. So that's the case. Okay, the other step in this part is going to be entanglement swapping. Entanglement swapping is just a protocol for changing, or for, how do you say this? Entanglement transmission between distant parties, right? In this case, we assume that you have an entangled state held between Alex and Charlie, and then another one between Charlie and Bob. And you can, by making measurements in the intermediate party, then you can recover an entangled state between Alex and Bob. And this is going to be useful if you're considering a theory of quantum repeaters, but it's not going to increase the entanglement of the state. That's for sure. Okay, let me show you with the states that we have been using, let me show you the improvements in negativity for photon subtraction. Okay. So, as you can see, the asymmetric and the symmetric cases have different negativities, of course, because of the different configurations. This case, we can see the negativity of the asymmetric case almost goes to 350 meters, but the one with the symmetric state goes to 300 meters. That's the thing. Heuristic photon subtraction, well, maybe it's easier to see here. Heuristic photon subtraction is going to work better always for the symmetric case, for the symmetric state, not for the asymmetric state. In this case, if we're considering symmetric photon subtraction, right? Same number of photons, subtracting the same number of photons in one mode and in the other, the symmetric protocol is going to work better in the symmetric state. The thing is, this gives us an idea of how these states are going to behave, but this is not going to be the full picture, because it's going to be a different thing depending on the quantum protocol that we want to implement. So, in order to illustrate how these states can be used or can be useful, we will look at quantum teleportation. Quantum teleportation in this continuous variable setting is just an adaptation of the original quantum teleportation protocol, right? In that case, you had a qubit state that you want to teleport. You had two parties sharing a Bell state, an entangled Bell state, and then the party that held the state to be teleported, the target state, and a mode of the entangled resource, did measurements on the maximally entangled basis. So in this case, the Bell basis, and then communicated the results classically to the other party. In this case, the state that we're going to look at is just a coherent state, The entangled resource is going to be a Gaussian state held between Alice and Bob. In this case, we represent here the generation of a two-mode squeeze vacuum state with photon subtraction, just for illustrative purposes. And then with the coherent state and one of the modes of the entangled state, Alice is going to do homodyne detection. It's going to be measuring on the maximally entangled basis. It's going to obtain quadratures of the state that is going to communicate classically to Bob, and then Bob is going to apply a displacement on the mode that he holds. Right? The average fidelity will compute in this way. And if we have a Gaussian entangled resource, we have a simple formula for the fidelity average over all measurement outcomes. Right? This is going given just with the submatrices of the covariance matrix that describes the entangled resource. And this identity is the covariance matrix of the coherent state. So, looking at the fidelities, when using the entangled states that we have seen distributed through OpenAir, we see again same thing as the negativities, right? For the symmetric state, you can have heuristic photon subtraction that is going to be better than just the bare state, the two-mode squeeze thermal state that we had initially. If you can see, we do probabilistic photon subtraction, which is what is going to be accessible in the lab. You can have an advantage for low distances. I mean, then it's going to be worse. Then this can represent an advantage if we're going to, use quantum repeaters, or, I mean, for connecting different chips or quantum processors in the lab. Then, about entanglement swapping that I mentioned earlier, that does not give you an advantage in entanglement, it does give you an advantage in fidelity. It does extend the reach of the fidelity. Sorry I didn't mention before, these red areas represent the region in which the quantum advantage is lost, because the maximum fidelity that you can obtain with a classical teleportation protocol is 0.5. So any fidelity that crosses into this red zone has lost all the quantum advantage. So we're interested in the behavior out of that region. So yeah, so here comparing all the best protocols that we have for overcoming this open-air degradation and entanglement, we see that while photon subtraction can give you an improvement early for short distances, entanglement swapping, what it can do is extend the reach of entanglement, although for very low fidelities. Okay, so to sum up all the things that we have seen, I've shown you that an efficient protocol for open-air entanglement distribution with microwaves goes through first having entangled states that can be generated with JPAs and can be two-mode squeeze thermal states, which are the easiest states to generate and are the most realistic, given that we're considering this thermal radiation present. Okay, so after the state generation, you need to transport those states into open air, and that's how that's where the quantum antenna comes into play. Then in open air, we describe through an attenuation channel how these states are thermalized and suffer photon losses, and how entanglement is degraded. We have seen the maximum distances that entanglement can survive in open air. And then we have seen photon subtraction and entanglement swapping, how they can overcome this degradation. And finally, we have studied the paradigmatic case of quantum teleportation. As the perspectives for this work, we're working right now on quantum communication between satellites because of the security that quantum communication brings. Then we can reduce the energy requirements. Also, the environment effects are going to be reduced. and it's easier to achieve state generation because the temperature is reduced, so it's easier to maintain cryogenia. But then we have to consider free space path losses, possible polarization effects, and scintillation and things like that. It's going to be better for satellites being in the same orbit, not for Earth to satellite communication. That's probably going to present challenges when describing the attenuation in that scenario. And also there are going to be Doppler effects due to the relative speeds of satellites. Also some other things that have to be done are the design of the receiving antenna, because we have only designed the emitting antenna. We have to study diffraction in the emitting antenna because we are considering just directed transmission of the signals in open air. We have to implement more solid protocol for quantum repeaters, and this goes through investigating other photon subtraction protocols using advances or current advances in microwave technology. For example, the itinerant microwave photon detection and trapping that I presented, I think, a couple of weeks ago as the paper in these weekly meetings. So this is the end of my talk, and I hope you have questions. Thank you very much.
I have a question.
Okay.
Can you realize the heuristic photon subtraction in the lab, or?
I mean, not technically, no. So, I mean, the thing is that you get close to the heuristic photon subtraction as you increase the transmittivity of the beam splitters, right? I mean, in the effects that it has on the negativity of the state or the fidelity of the state. But then the probability of getting that result is going to be reduced. I mean, if you set tau equal to 1, the probability goes to 0. But at the moment, we're investigating other ways to do this. As I said, with this work by, I don't remember the name. There's some French people that developed this detector for traveling microwave photons that can be used, I mean, for doing photon subtraction. There's going to be probably a more efficient way to do this. This protocol that we have been using is just an adaptation from an optics protocol. So I think, yeah, using existing microwave technology can bring some advantages to this. I don't know if you can achieve the efficiency or the increase in entanglement or fidelity that you have with the heuristic one, with the theoretical one. There's going to be probably some trade. Maybe the efficiency is not the best one, but maybe it's you lose this non-deterministic nature of the protocol. I don't know. I'm just guessing. I'm not sure.
I have a question.
Okay.
Yeah, you said that this satellite Earth communication would be really difficult to study, right? But if I'm not mistaken, satellite Earth quantum communication has been experimentally achieved, right? So can you?
Yeah, for sure.
So what's the difference, or because they didn't do entanglement, or what?
No. I mean, yeah, I mean it has been achieved, and I'm not saying that this, our method or anything is going to improve improve it. I'm just saying we're looking into satellite quantum communication. We're looking at the satellites or communication between satellites in the same orbits. I was just rambling on about how it's going to be, or it may be more difficult to model or to describe, because in this work, the attenuation channel that we have used considers isotropic environment, right? And in this case, you're going to have a gradient through different environments, different layers in which the attenuation of signals is going to be different. And yeah, I mean, I was talking about our theoretical perspective.
Okay, thanks. So it seems I have no more questions. So
Thank you very much.
okay.
Okay, now let me do a thing.